rate. To obtain the rate of a reaction, you must determine the concentration of a reactant or product during the course of reaction. There's several procedures to do that, several ways to do it. One method for slow reactions is to withdraw samples from the reaction vessel at various times and analyze them. That has to be a pretty slow reaction. You remember, as I go to take a sample and I walk to go bring it to an instrument, that rate's changing if it's a very fast reaction. So it's got to be something extremely slow if I'm going to do that. More convenient way are techniques that are continuously monitoring the progress of a reaction based on some physical property or system. So basically, as the reaction's going, you got something monitoring that actual reaction based on some property of some sort. A couple of examples of that we'll see on the next slide. Gas phase partial pressures is one way they do it. You have a manometer reading, provides the concentration of species during the course of the reaction based on partial pressures. You may recall PV is equal to nRT, the ideal gas law, okay, which basically means pressure then is proportional to N over V, or concentration, okay, number of moles over volume, okay. So basically, by monitoring the pressure, there's a relationship between that and concentration, and then we can go from concentration to figure out rate. Another way is colorimetry. Species that absorb near UV light, the intensity of your absorption is proportional to the concentration of your species. So you know absorption is proportional to some concentration of the species. Then from that, you can use that absorption rate to determine the reaction rate. Okay, this is related to Beer's law type problems. Let's talk about the relationship between rate and concentration. Experimentally, it has been found that the rate of a reaction depends on the concentration of certain reactants, not always all reactants. What I mean by that is some reactants may have no effect on rate. It has to be present for the reaction to happen, but it has no effect on rate, as well as any catalysts. Catalysts are things that speed up the reaction, so obviously that has an effect on rate. Now, if we design our experiment well enough, we'll be able to determine the effect that one concentration has on the rate of the experiment. Let's look at the reaction between nitrogen dioxide and fluorine to give us nitrofluoride. You have two nitrogen dioxides plus one fluorine, gives you two nitrofluorides. Now, if I design an experiment, I can determine the effect that the change in the concentration has on the reaction rate. For instance, say I held the concentration of my F2 constant in two different experiments. Okay, I have the NO2 concentration and my F2 concentration in one experiment. Then I come back and I run a different experiment where I double the concentration of NO2, but I leave the concentration of F2 exactly the same as it was before. Well, any change in my rate of my experiment will be due to that change in concentration of NO2. If I do that, I'll find out that if I double the concentration of NO2, I double my rate. If I triple the concentration of NO2, my rate triples. What I see is there's a linear relationship between NO2 and the rate while I'm holding the concentration of F2 constant. So the rate of this reaction has been observed to be proportional to the concentration of nitrogen dioxide. If I change the concentration of nitrogen dioxide, my rate changes proportionally. So when the concentration of nitrogen dioxide is doubled, the reaction rate doubles. There's a linear effect. If I triple it, the rate triples. This is what I observed by designing my experiment. Well, now I can also do the same thing and look at the fluorine and see how that affects the rate. So I'm going to hold the nitrogen dioxide constant in my experiments, but change the concentration of fluorine. Now, if I double the concentration of fluorine, once again, I see that we double the rate. If I triple the concentration of fluorine, I find out that the rate triples. So once again, there's a linear effect there. Well, since I can determine these changes as I change concentration, what happens to rate, there must be some mathematical expression to relate the two, and there is. So we're going to show you next is the mathematical expression that relates the rate of a reaction to the concentration of reactants. Okay, next we want to talk about the relationship between rate and concentration. Experimentally, it has been found that the rate of a reaction depends on the concentration of certain reactants, not always all reactants, as well as the catalyst. Now, what do I mean by not always all reactants? Well, there may be some reactants that must be there as part of the reaction, but it has no effect on rate. Okay, it has no effect on changing rate. If I change the concentration of the reactant, as long as I have some, the rate will remain the same. If you design an experiment well enough, then what you can do, you can determine how the concentration of one reactant is changing the rate of the reaction. So you hold some species constant while you change another one and see what happens to the rate, and that tells you how rate is being affected by that particular reactant. Let's look at a reaction of nitrogen dioxide with fluorine to give nitrofluoride. You got two NO2s plus an F2 gives you two NO2Fs. Okay? The rate of the reaction has been observed to be proportional to the concentration of nitrogen dioxide. What that means is, if I hold the concentration of fluorine constant and change the concentration of NO2, say double the concentration, I find that the rate doubles. There's a linear relationship between the concentration of NO2 and the rate. And I found that information out by designing an experiment that allows me to see that. When the concentration of nitrogen dioxide is doubled, the reaction rate doubles. There's a linear effect. Okay, if I triple the concentration of nitrogen dioxide, the rate triples. I see this effect as long as I chose the right experiment. Okay, by holding the concentration of fluorine constant. Now I can do a similar experiment, but now let's hold nitrogen dioxide constant and change the concentration of fluorine. And I notice when I do this in the experiment that when I double the concentration of fluorine, I double the rate. Okay? Once again, it also has a linear effect. If I triple the amount of fluorine, the rate triples. There's a linear effect. Since they have this relationship, there must be some mathematical expression to relate that rate of the reaction to the concentration of reactants. There is, and it's called the rate law. A rate law is an equation that relates the rate of a reaction to the concentration of reactants and catalysts if there's one raised to various powers. So going back to our experiment, the 2NO2 plus fluorine gives you the 2NO2F. Okay, the rate will be equal to K, concentration of NO2, times the concentration of F2. Both of these are raised to the first power, okay, because we said there was a linear relationship between them. That K is called the rate constant, and it is a proportionality constant in the relationship between rate and concentration. Basically, when we say that we double the concentration of N2 and the rate doubled, it's a proportionality. Okay, by having that proportionality constant K, now we can set that equation equal. That power, that one coefficient, that one order for this NO2 and the one for this F2, those are understood right now. Those are called the orders of the reaction. And those are determined, as I said, experimentally. They are not coming from the coefficients of the balance equation. They do not come from that. They come from experimental data to determine those orders or those reactants. As a more general example, consider the reaction of a substance A and B to give you D and E. Okay, I have a generic equation where my small letters mean my coefficients and my large letters mean my substances, and that C over the arrow is the catalyst. Okay, I can write a generic rate law expression of this, all in terms of reactants and catalysts, all raised to some power. I can write the rate law to look something like this. Rate is equal to some constant K, concentration of A to some power M, times the concentration of B to some power N, times the concentration of C to some power P. Okay, that M N, and P, those are all called the reaction orders with respect to those reactants. Those are determined experimentally. Okay, those are determined experimentally. They don't become from the coefficients of that balance equation. Okay, that balance equation is a molecular equation. Okay, which is based on moles. It may not be giving you the actual equation that's going on by collisions. Okay, there may be side reactions. There may be several steps to the reaction, and those orders are coming from the slowest step. The slowest step will dictate how fast the reaction can go, and that will dictate the orders in your rate equation. The exponents m, n, and p are frequently, but not always, integers. Okay, they must be determined experimentally and cannot be attained by simply looking at the balance equation. You got to remember that balance equation is based on moles, not collisions. The mechanism behind that reaction, okay, the steps involved, are based on collisions, and that slowest step is what's going to dictate your rate equation, okay, and the orders with respect to those species. So let's define reaction order. The reaction order with respect to a given reactant species equals the exponent of the concentration of that species in the rate law as determined experimentally. Okay, going back to our example, okay, that 1 for the NO2 that I said was a linear reaction, that F2, that was to the first power, those are the order of the reactants. Okay, for N2 it's an order of 1, for F2 it's an order of 1. Now typically we do not put the 1, we got that understood if it's there, that it's a power of 1. The overall order reaction equals the sum of all the orders of the reactant species in the rate law. So for this example here, I would take that power of 1 for NO2 and that power of 1 for F2, add them up, and that tells me that the overall order is a second order. If you go back to my generic example with the M, N, and P, you add those up, the overall order would be M plus N plus P. Consider the reaction of nitric oxide with hydrogen according to the following equation. 2 NOs gives you 2 H2s, gives you 8 N2 plus 2 H2Os. Experimentally, they did an experiment where they held some things constant and some things they changed. They determined that the rate law was equal to rate equal to K, the concentration of NO to the second power, the concentration of H2 to the first power. Notice that the power of H2 does not equal the 2 that's in the reaction. Okay. Once again, you got 4 molecules there. The probability of 4 molecules colliding at the same time was slim to none. So most likely there's a mechanism to this. There's a several step process. That slowest step in that process is what dictates the order, and that's where the 2 is coming from for the NO and the 1 is coming from the H2. That slowest step in the mechanism, and by designing our experiment we figure out what those orders are. Okay. Thus, the reaction is second order is NO, first order in H2. Okay, not the 2 as in the molecular equation, because this is not an elementary reaction. It's not based on collisions. Okay, the overall order would be the 2 plus 1, which would be third order. Okay, reaction orders. Although reaction orders frequently have whole number values, particularly 1 and 2, which we run into a lot with whole number values when we're doing our calculations in lecture, they can also be fractional. There also can be 0 and negative orders as well. They are also possible. 0 is a little bit more common, what we're going to see as we work problems. Let's talk about 0 a little bit more. The concentration of reactant with a 0 order dependence has no effect on the rate of reaction. It has to be present in the experiment, but it has no effect on rate. If I double that concentration, the rate stays the same. If I triple that concentration of that species with 0 order, the rate never changes. Okay? But it has to be present for the reaction to go. As long as some is present, the reaction will continue on, but it will have no effect on rate. Let's go a little bit more detail on 0 order, since we will encounter it some. What What's happening is you have several step procedure. Okay, for instance, you have A plus A gives you A2. Okay, and let's say this is the slowest step of a reaction. That A2 molecule now collides with B and forms C and D. And let's say that step 2 goes pretty fast. Overall, the reaction seems to be, since the A2 molecules cancel out, 2A plus B gives me C plus D. Okay, A and B never actually collide. Okay, what we're given the overall equation is a molecular equation. The rate law, when we do this problem, look at it experimentally, turns out to be rate is equal to Ka to the second power. Well, where is this A to the second power coming from? What's dictating the overall rate equation is that slowest step. If you go back to that slowest step, you'll see there's two A molecules that are based on collisions. Got an A molecule hitting another A molecule, and that's where that superscript 2 is coming from, that order of that reactant's coming from. So when we do our experiment and compare the data, we're actually finding out that slowest step and what are the orders associated with that slowest step, that elementary step. So note, B is zero order and is not part of the rate law because it's not part of the slowest step, and that's how we get B to the zero order. Determining the rate law. One method for determining the order of a reaction with respect to each reactant is the method of initial rates. It involves running experiments of multiple times, each time varying the concentration of only one reactant and measuring its rate. Selective data is what we're doing. We're basically going to run the experiment, hold something constant, change something, so we know whatever we change is affecting the rate. The resulting change in rate indicates the order with respect to that reactant. Okay, so we're going to change the concentration, see how that affects rate while holding other species constant. If I double the concentration and the rate doubles, that's a linear relationship telling me it's first order. If I double the concentration, I quadruple the rate, that's a second order. So that allows me to determine my order with my species. So if doubling the concentration of a reactant has a doubling effect on the rate, then one would deduce that it is a first order dependence. Same change in concentration occurs to the rate. Basically, a power of 1 is occurring. There's a linear relationship. So you can see, I double the concentration of something. 2 to some power time r gives me a double the rate. Okay, so the question is, what 2 to what power will give me that 2r? That's the first power. Anything to the first power equals itself. So this is a first order reactant. So this is first order. Okay, so we symbolize it with a 1. If I triple this species in its first order, then what's going to happen is the rate's going to triple. If I quadruple it, quadruple the rate. There's a linear effect. So my order is 1. If doubling the concentration has a quadrupling effect on the rate, one would deduce its second order. Basically, the square is happening to the rate as opposed to the change in concentration. So if I double the concentration of the species, okay, 2 to the some power time r will give me 4 times the rate. Okay, in this case, for 2 to something to equal 4, b squared. If I triple the concentration, then what's going to happen is 3 squared give me 9 times the rate. Okay, the square happens to it. If I find doubling the concentration results in an 8-fold increase in the rate, this will be third order dependence. The cube is happening to the rate as opposed to the concentration. So you can see if I double the concentration of C, 2 to some power of r gives me 8r. Okay, well, 2 to the cubed. The cube is happening. Say I triple it, triple the concentration. What kind of rate am I going to have if it's third order? Okay, well, if I triple the concentration, then 3 to the third is going to happen, which means I'm going to see 27-fold on my rate. The cube's going to happen. If doubling the concentration has no effect on the rate, one would deduce that it is a zero order dependence. Well, what to the power, 2 to what power will give me just that rate? okay, well 2 to the 0, okay, anything to the 0 power is equal to 1. So if I triple it and the rate stays constant, it's a 0 order. Homework, okay, homework. Number 6, ask you questions about order, okay, and questions relating to doubling concentrations, what would happen to the rate type questions.